Assalamualaikum warahmatullahi wabarakatuh. Hello everyone. Introduce you from group 6, which consists of Wenda Yuzarima, Nur Octaviana, and Yuli Andini. Here we will convey the result of our work, namely a review of a chemistry journals with topic catalyst. Have a good time watching ya. See you. Okay, good for the first journal, namely the journal with the title Green Synthesis of Cis-Bacid by Using Natural Acid Catalyst by Yadav Garima, Gio TV, and Mani in 2015. As for the abstracts for this journal, in brief, namely, the objective of recent research work has also used green methodology for synthesis of seed base. Conventionally, synthesis of seed base is carried out with or without acid catalyst and sometimes by reflux the mixtures of aldehyde or ketone and amine in organic medium. Present synthesis involves the use of fruit juice of Citrus limata, Vitis lanata, and aqueous extract of Mangifera indica as natural acid catalyst. The synthesis product was identified by its physical properties, melting point, TLC, and characterized by mass spectrometry. With keyword in this journal that is green chemistry, Cis-Bacid, natural acid catalyst, mass spectrometry. The next part of the introduction part of these journals. Green chemistry is the branch of chemistry that involves tools, technique, and technologies, development of more eco-friendly and efficient products which may also have significant financial benefits. It is a new way of looking at organic synthesis and the design of drug molecules, offering important environmental and economical advantage over traditional synthesis process. The recent interest in green chemistry has posed a new challenge for organic synthesis in the new reaction condition need to be found with reduce the emission of volatile organic solvent and the use of hazardous toxic chemicals. They improve selectivity, reduce reaction time, and simplifies separation and purification of product than the conventional methods. Seed bases known as imine are compounds containing a xanthine group, OCN, and represented by the general formula R3, R2C, and R1. They are the condensed product of aldehyde or ketones and were first reported by Hugo Schiff in 1864. The Schiff's base derivatives have been extensively investigated for more than a century and employed in different aspects including magnetochemistry, nonlinear optics, photophysical studies, catalysis, materials chemistry, chemical analysis, absorption, and transport of oxygen. Due to this beneficial property, concern for the environmental demand, and strong interest in the development of green chemistry, new sustainable catalysts and new environmentally benign process have been investigated which are both economical and technological feasible. Recent study also involves some eco-friendly and inexpensive natural catalysts like grapes or Vitis lanata juice, sweet lemon or Citrus limata juice, and aqueous extract of mango or Mangifera indica for synthesis of Cis-Bacid. As for the literature survey in this research journal as shown on the screen, while the material and methods in this journal are A. Preparation of catalysts. Grapes with lime and unripe mango fruit were processed locally, then grapes were pressed into fruit juicer and filtered with cotton to get liquid juice. While sweet lime fruit was peeled off with knife and fruit slices were pressed into fruit juicer to get semi-solid. B. this synthesis of seed bases with grape juice, with lemon juice, and aqueous extract of unripe mango under solvent-free conditions by stirring method. Okay, result and discussion. In this work, the protonation of heteroatom in organic transformation was done with natural acid fruit juice. All the fruit juices contain many organic acid like citric acid, tartaric acid, malic acid, oxalic acid, succinic acid, and amino acids among these organic acid. The citric acid is the major constituent in many fruit extract. Thus, these organic acids are responsible for acidic nature of fruit juices and provide a desirable pH to catalyze the condensation reaction have used in the synthesis of seed base. Yield of the N-benzylidene aniline or SB1 and 4-chloro and benzylidene aniline or SB2 in the presence of the different catalysts by grain catalysis which have been used and good to excellent yield of the product was obtained. Catalysts are effectively catalyze the synthesis of seed base, and even very small amount of natural acid provide quantitative yield of the product. This is the table 1 comparative yield of N-benzylidene aniline and 4-chloro and benzylidene aniline in the presence of different catalysts. From this, the perspective has been clear the yield of the seed bases independent upon the electrophilicity of carbonyl carbon of benzaldehyde and nucleophilicity of aniline. Electrophilicity of benzaldehyde increases if any electron attracting substituent group attached to it and decreases in benzaldehyde has any electron donating group in this structure while the nucleophilicity of aniline increases due to electron donation group and decrease in the presence of electron withdrawing group. 4.1 Effect of catalyst loading on the product yield different yield of the product obtained with variable amount of acid catalyzed are summarized in table number 2 and table number 3. And this table 3 yield of the 4-chloro and benzylidene aniline obtained with different amount of natural acid catalyzed. The data currently sorted on increasing the amount of acid catalyzed product yield were decreasing because of acid concentration cannot be too high due to the basicity of amine. If the amine is protonated and becomes non-nucleophilic, equilibrium is pulled to the leaf and carbinolamine formation cannot occur. Therefore, many seed bases syntheses are carried out at nearly acid pH. 4.2 Characterization of the product. Both of the product are stable at room temperature and not hygroscopic. They are decomposed at high temperature, insoluble in water and soluble in ethanol. Thus, characterization of product was done with its physical properties, melting point, TLC, and mass spectra. Spectral characterization, it is done with mass spectra of the product. Mass spectra of N-benzylidene aniline so a molecular ion peak at 182 with 100% relative abundance, so it is also the best peak of spectra which correspond to the one additionally molecular weight of the synthesized compound because calculated molecular weight. The following are mass spectrometry results from research in this journal. Summary and conclusion. The recent work focused the importance of fruit juice as natural and biocatalyst in organic transformations. The catalytic activity, including the application of fruit juices in various organic transformations such as formation of CNC, CRN, born in different synthetically important organic compounds have been studied. Okay, strength and weakness in this journal. Strength. This journal provides an explanation regarding the good use of natural acid catalase with several reinforcement materials obtained from various surveys. The result and discussion in this journal are summarized into one complete discussion subject and also explained, which is also accompanied by other supporting pictures as research data. And weakness. The weakness in this journal is that it does not explain in the detail the result of observation or research development at each step in the method used. The following is a reference to the journal we reviewed.
Okay, for the second, I'm Nur Octaviana with student ID 1913023030 with the title of the journal is Study on Catalytic Scientists of Azodicarbonamide with hydrogen peroxide as a green oxidant. Volume and page is volume 8 and page 164 until 172. Years of published is 2021. Authors is Elahe Bohluha Bandi and Parviz Ahbadi Afal. With reviewers with Wendayo Zarima, I'm Nur Octaviana and Yuli Andini. Next is abstract. This study relates to an improved method for the preparation of azodicarbonamide, which is useful as a chemical blowing agent. Azodicarbonamide is prepared from the oxidation reaction of hydrazodicarbonamide or biurea with hydrogen peroxide as a green oxidant in the presence of a potassium bromide as a catalyst. Biurea also is prepared by reaction of urea and hydrazine. The prepared product have been characterized by FTER and TGE or DIC by series of comparative experimentals. Factors of influencing the yield of azodicarbonamide are studied, such as the amount of oxidant and temperature of reaction solution. Under the optimum process condition, the yield of azodicarbonamide can reach over 95% with hydrogen peroxide oxidation process. And the keywords is azodicarbonamide, hydrazodicarbonamide, green oxidation, hydrogen peroxide oxidation, and then catalyst. Next is introduction. Azodicarbonamide or ADCE is a yellow powder and widely used in industry as a foaming agent in the production of various products because its decomposition products are non-toxic, odorless, and non-pollution. The gas from the ADCE decomposition are 16.5% nitrogen gas and 24% carbon monoxide, 5% carbon dioxide, and 5% ammonia. The third process of ADCE is a falling hydrazodicarbonamide or biurea is synthesized from cyanide, hydra, and urea by means of acid condensation reaction, and ADCE is a synthesis from biurea through oxidation reaction. There are several processes for production azodicarbonamide by the oxidation of biurea. It can be divided according to different methods. Use the term oxiding agent, Claude method, chlorine method, and hydrogen peroxide process. With this method, the only byproduct is water, no pollution. The dose of the H2O2 is easy to control. The product has stable quality and yield, so the method is a lot of advantages, such as no dangers of explosion, no pollution, no by-production, high product quality, and high yield. Next is material and methods. Material is urea, hydrogen peroxide 30%, and sodium bromide were obtained from mercs. Other materials were of chemical reagents grades and were purchased from Sigma authorized of FLEUKA companies and trades when necessary. And then method number 1 is general product for scientists of urea. It is 5G or 0.03 mol of hydrazine sulfate, 5.4 G or 0.08 mol urea, and 100 ml of water was heated to the revolution temperature under revolution condition and with agitation. After about 2 hours of boiling with adding some sulfur acid that was added dropwise to hold the pH at a level between 2 and 2.5. The reaction was discontinued at the end of 5 hours total elapsed time. The reaction mixture was then cooled and filtered, and the filtered precipitate was washed with water. Method number 2 is general production for the preparation of azodicarbonamide by oxidation of urea with hydrogen peroxide. It is 2.3 G or 0.02 mol of the urea was suspended in the some water and 0.6 mol of potassium bromide as a catalyst was added. The pH was down to less than 2 with adding some sulfur acid. The suspension of held to the Clausius reaction temperature, and after the pH value had been adjusted, 0.08 mol of hydrogen peroxide was added. After the oxidation increased, the reaction mixture was tried from 30 minutes in a straight water bath from yellow ADCE deposit. The filtered the product as washed several times with distilled water. Next is result and discuss ER spectra of ADCE and urea. I'll show in figure 1 their ER of ADCE and urea has been compared. The ER belt assessment of ADCE and urea are listed in the table 1 in the slide. FTER spectra agree with the standard spectra of urea and azodicarbonamide indication that the production are urea and azodicarbonamide. Okay, the second is thermal analysis of ADCE. 3G and DIC curves of ADCE are presented in the figure 2. Pure ADCE has 3 peaks corresponding to 3 moles slope step in the 3G curves. There is a sharp endothermic peak 220 in the DIC curve with a loss of about 75 in the 3G curves. At the end of analysis, the sample was reaction to 0. And then the last is catalyst oxidation of urea to ADCE with hydrogen peroxide. The effect of H2O2 contraction on the oxidation of urea has also been studied on the table 1.3. The H2O2 contraction used were 0.006 and 0.09 mol, while the amount of urea was kept fixed. It is clear from table 1 that the percentage of ADCE yield increases with increasing the H2O2 content. In the general, it is appropriate to use H2O2 axis of the stoichiometry required amount of 1 mol per mole of p-urea. Examine the effect of temperature on the yield of the product. The experimental results are shown in the figure 3. The figure 3 shows that with an increase of temperature, the yield of ADCE increasing when after reaction for 600 and further increments of temperature can slightly decrease the yield. This is made due to thermal decomposition of H2O2. The last is conclusion. It can be concluded that this catalyst system is highly efficient for oxidation of B-urea to ADCE with hydrogen peroxide as an environmentally friendly oxidant. Oxidation of KBr as a catalyst to the B-urea or hydrogen peroxide system led to a remarkable increase in the yield of ADCE. In this work, by optimization of reaction condition, factors of influencing the yield of azodicarbonamide were studied. Under the optimum process condition, the yield of azodicarbonamide reached over 95% with hydrogen peroxide oxidation process.
And the next review journal, title of the journal is Preparation and Evaluation of NeAl2O3 Catalyst Promoted by Alkaline Earth Metal in Glycerol Reforming with Carbon Dioxide. Year of published is 2021. Author is Masao Tevanarat, Mahrez Rezai, Fareh Teh Mahkani, and reviewers is Wenda Yuzarima, Nur Octaviana, and Yuliandini.
Abstract: Glycerol is the main byproduct in the biodiesel process and can be considered as a promising and renewable source of hydrogen generation through the reforming process. In the work, catalyst with 15% Ne supported on 3% Al2O3, M1 quadrat, MgO, JaO, SRO, and BaO were prepared and employed in the glycerol dry reforming or GDR reaction to produce hydrogen and carbon monoxide. The textural characteristics of the fresh and sped catalysts were determined using the ACP, BET, TPR, TPO, and SEM analysis. Based on the obtained result, the catalyst promoted by SRO had the highest catalyst activity. The result indicates the adding various alkaline earth oxide into the catalyst support. Introduction: The environmental concern caused by fossil fuel combustion made biomass one of the most promising and vital energy resources. This is due to the significant hydrogen production. Glycerol is the main byproduct of the biodiesel industry, which is produced from vegetable oil or animal fat transesterification. Furthermore, glycerol is a non-toxic, volatile, and non-flammable chemical, which is an ideal source for power application. Various reforming processes such as carbon dioxide reforming, steam reforming, aqueous phase reforming, radial oxidation, and autothermal reforming have been reported of hydrogen as production from glycerol. It is noteworthy to mention that methane is a not renewable resource. Hence, glycerol might be an alternative chemical compound due to its renewability.
Catalyst preparation. A two-step impregnation method was applied for the preparation of the 15% nitrogen catalyst promoted with 3%. Characterization: the X-ray powder diffraction or XRD technique was performed on the analytical spectro instrument. element analysis of promoter was performed using atomic absorption spectrometry on the GBC instrument. Catalytic test. The performance of the catalyst in the glycerol carbon dioxide performing was evaluated at 1 atmosphere in the fixed bed tubular quart microreaction. The microreaction was placed in the electric furnace and the key type couple was located inside the reaction. At the bottom part from the catalyst that controls the reaction temperature. Result and discussion. Effect of various parameters. Physicochemical characterization of the 15 nickel/3M2O3 catalyst. X-ray powder diffraction analysis. X-ray crystallography of the 50 nickel/3M2O3 catalyst. CaO, which may be due to the low content of promoter. For the catalyst promoter with SRO and BaO, two small diffraction peaks were observed in the XRD pattern. This could be related to the SR3 Al2O6 and Ba2 Al2O5 phase. The nitrogen absorption or dispersion isotope of the promoted nickel catalyst calcined at 150 Celsius. Next, the reduction behavior of the promoted Ne catalyst was studied using the TPR that can be observed in fake. The 15 Ne/3M Al2O3 catalysts have two major reduction peaks. Observed peak at temperature lower than 7 Celsius are attributed to the phase transition of the NEO phase to Ne. It strongly interact with the catalyst support. Conclusion. The Ne/Al2O3 catalyst promoted with 3% alkaline earth metal oxide or MgO, CaO, SRO, and BaO were produced. The investigate in the carbon dioxide reforming of glycerol where the catalyst activity require the temperature of 600 until 700 Celsius. Catalyst activity of 15 Ne/3SRO Al2O3 decreased rapidly in the first 300 min, the slowly up to 1200 min where the experiment was stopped. Strength and weakness. Strength. The advantage of the research and experiment is that it can show the precise evaluation of the Ne/Al2O3 catalyst promoted by alkaline earth metal in the reformation of glycerol with carbon dioxide by using part and course. Weakness. The weakness of the experiment and research is that very high accuracy is needed so that there are no errors in calculation. Reference of the journal is Masud Tefanarad Mahrezrezek vs. Tehmaskani 2021. Preparation and evaluation of Ne/Al2O3 catalyst promoted by alkaline earth metal in glycerol reforming with carbon dioxide. International Journal of Hydrogen Energy.